and welcome back to my channel. Today I'm going to be doing a COMSOL tutorial on vacuum drying. Alright. Okay, so here's some background information on the theory. Vacuum drying is a chemical process frequently used in the pharmaceutical and food industries to remove water or an organic solvent from a wet powder. When designing a vacuum drying system, engineers aim to minimize the drying time while maintaining high quality in the product. Okay, so the model investigates vacuum drying in a niche. I don't know if that's how you say that. Niche filter dryer, which consists of a cylindrical drum filled with wet cake as seen in figure 1. The top of the cake is exposed to a low pressure headspace and the side and bottom walls are exposed by heating fluid. By operating at a very low pressure and an elevated temperature, the evaporation rate of the liquid increases, thus accelerating the drying process of the powder. By modeling the heat transfer and evaporation of the solvent in the powder, the temperature and liquid phase profiles can be studied. This example is based on the paper published by Muru and others for powder dried with N-propanol under static conditions. So here's the graphic describing our model. Alright, so axisymmetric, meaning it's in a cylinder, symmetric about the z-axis. So we're looking at half of the cross section through the center of the cylinder. So you can imagine the center is a wet cake. There's dry cake that's being dried by contact with the heat from the surrounding wall, the containing wall. And then outside the vacuum drying chamber wall, we have a heating fluid. So a fluid might be a gas or a liquid. We'll see. So for our model definition, the cylindrical cake can be modeled using a rectangular geometry and a 2D axisymmetric component. The cake radius is 40 centimeters and the cake height is 10 centimeters. The vacuum drying process involves heat transfer and vapor transport and modeling the evaporation of the solvent. The equation, so for liquid phase evaporation, the equation and the coefficient form P to E interface solves for the volume fraction of liquid, or theta L, in the cake. Okay, so we've got the partial differential of the volume fraction of liquid with respect to time equals del of dL, the apparent liquid diffusion coefficient, times del of the volume fraction of liquid, minus mLg, which is the evaporation rate, over rho L, or the liquid phase density. All boundaries are prescribed as no flux conditions. The evaporation rate mLg is related to the difference in the equilibrium vapor pressure of the gas in the cake, P star, and headspace vapor pressure, Pg, with mLg equals K vape, or the evaporation rate constant. mLg is the evaporation rate constant times rho L times P star minus Pg, or the difference in pressure between the equilibrium vapor pressure and the headspace vapor pressure, over Pg, the headspace vapor pressure, if theta L is greater than 0. And theta is the volume fraction of liquid. As long as we have some liquid left in the cake, we're saying this equation applies. And when there's no liquid left, and once all the moisture has sublimated, there's nothing left to freeze dry, then we have mLg, m dot, so that tells you it's a rate, Lg equals 0 if theta L is less than 0, or P star is less than or equal to Pg. And we're going to have a headspace pressure, or the vacuum pressure surrounding the cake, set to 15 millibar, so very, very low pressure. Evaporation should cease once the value of liquid phase reaches 0, fully evaporated, or if the local vapor pressure does not exceed the headspace vapor pressure. So then there's no driving force for the evaporation. In the model, step functions are used to smoothly ramp the evaporation down to 0 under these conditions. The equilibrium vapor pressure of N-propanol, which is related to temperature, can be found using Antoine's equation. P star equals 10 to the power of A minus B over C plus T, where A, B, and C are constants found in reference 2. The solvent migrates in the cake due to capillary flow. Instead of directly solving for the velocity field of the liquid phase in the porous media, the transport of the solvent through the cake can be approximated as a diffusion process. Therefore, when there's a gradient in the volume fraction of solvent, the liquid phase migrates from the region with a high volume fraction of solvent to the region with a low volume fraction of solvent. The liquid diffusion coefficient is calculated with these equations. dl equals alpha times the difference in the volume fraction of liquid and the residual saturation, theta L star, if theta L is greater than or equal to theta L star. And dl equals 0 if theta L is less than theta L star. So alpha here is the proportionality constant, and theta L star is the residual saturation, both of which are determined experimentally in reference 1. When the volume fraction of liquid phase present is below the critical value, theta L star, the diffusion of the solvent in the cake should no longer occur. And a step function is used to smoothly ramp the diffusion coefficient down to 0 under these conditions. As the cake dries, the liquid phase evaporates and is replaced by gas between the solid particulates. The sum of the volume fractions of the 3 phases should equal unity. Therefore, the volume fraction of gas present, theta G, can be calculated with respect to the constant volume fraction of solid powder, theta S, and the variable liquid volume fraction, theta L. So the fraction of gas equals 1 minus the fraction of liquid minus the fraction of solid. Okay, for the heat transfer physics, our governing equation is going to be given by this. Rho effective is the density, effective density. Cp is the heat capacity. D temperature dt, the change in temperature with respect to time, equals del of the effective thermal conductivity times del temperature plus Q, which is the heat source. Energy is required for evaporation to occur, which is characterized in a heat source domain condition with Q equals negative m dot Lg, the rate of evaporation, times delta H evaporation, where delta H is the latent heat evaporation. The side and bottom boundaries of the filter dryer are exposed to a heating fluid. In this model, heat flux boundary conditions account for the energy transferred to the cake from 60 degrees C heating fluid given a heat transfer coefficient of 10 watts per meter squared per Kelvin. The cake consists of solid powder particulates, a liquid solvent, and a gas that fills the voids between the solid powder particulates. Therefore, the material properties of the cake must take into account the properties of the 3 phases in proportion to their presence in the cake. In this case, the effective density, rho effective, and effective heat capacity, Cp effective, are calculated with these equations. So we have contributions from the liquid, solid, and gas phases for each of these characteristics, the effective density and heat capacities. The effective thermal conductivity is calculated with lambda effective equals lambda dry plus theta liquid over 1 minus theta solid, the volume fraction So the effective thermal conductivity equals the dry thermal conductivity plus the volume fraction of liquid over 1 minus the volume fraction of solid times the difference in the thermal conductivities of wet and dry states. Here are the results we're going to generate. The following figures show the temperature, volume fraction of liquid phase, and the apparent moisture diffusivity in the cake after 30 hours. The temperature of the cake approaches the temperature of the heating fluid at the bottom and side boundaries. Because the liquid phase evaporates in the heated region, the volume fraction of the liquid cake is lowest near the heated side and bottom boundaries and highest in the center of the cake. So if we look at the results, we're going to generate the highest temperature is around the outside, which makes sense because that's where the heating element is touching it, or the heating fluid. And then the other plot we're going to create is the volume fraction of liquid after 30 hours. The zero liquid around the outside and residual amounts of liquid left on the top, which is where it's evaporating from. So liquid moves from the outside to the inner and upper part of the wet cake. We'll also create surface plots for apparent moisture diffusivity and evaporation rate. Hi, I'm back, and in a different outfit because it's a new day. So yesterday I went over the background theory information for the vacuum drying model. Today we're actually going to do the tutorial. So we're going to start with a model wizard and do a 2D axisymmetric model. For physics, we're going to choose heat transfer and solids. Add. And then we're also going to add a PDE interface, partial differential equations, which is under mathematics, PDE interfaces, coefficient form PDE, so the C parentheses, and study. Oh, in the text, in the field name text field, we've got to type theta. So we're overwrite the U with theta. And for dependent variables, enter the following settings, theta L. And in the source term quantity table down here, we're going to change the units to inverse seconds. And study. We're going to do a time-dependent study. Click Done. No. And I'll go ahead and save this as vacuum drying. Okay, so under global definitions, parameters 1, in the model builder window under global definitions, click parameters 1. In the settings window, locate parameter section, and we're going to load from file, which I already downloaded before. You can get from COMSOL's website, and the link in the description box. And we're going to upload vacuum drying parameters text file. So there's all of our global definitions parameters. And now we're going to add some definitions. Variables 1. In the model builder window under component 1, right click definitions and choose variables. So the first one on the drop down menu, and in the settings window, what did I do there? In the settings window, for variables, locate the variables section. Click load from file. And then we're going to upload vacuum drying variables text file. Alright, so we've got some yellow text here for functions that we have not defined yet. So once we define the function, then those will become black text instead of gold. Next, define two-step functions to smoothly decrease the evaporation rate and apparent moisture diffusivity to 0 as the solvent evaporates. So here's where we're going to define function step 2 and step 1. So for step 1 in the home toolbar, so up here we're already in home under variables, functions, choose global step. In the location text field, type 1.005. Click to expand the smoothing section at the bottom, and in the size of transition cell in text field, type 0.01. So it was set at 0.1 default, we're changing it to 1/10 smaller. Now we're going to add step 2. In the home toolbar, click functions, global step, parameters, and this time we're going to have the location at 0.005. And again, the size of the transition cell, we're changing to 0.01. Alright, and for geometry, we're going to add a rectangle. So I'm going to click on Geometry toolbar at the top, Rectangle, and in the settings, we're going to enter R0 for the width and H0 for the height. Those are definitions that were in the global definitions parameters. And click Build All Objects. So there's our rectangle. I'm going to go ahead and do zoom extent so the field of view is more to scale. And now we're ready to go to physics to define the boundary conditions, heat flux, heat source, etc. So we're starting off with heat transfer in solids, H2 module. In the model builder window, under component 1, heat transfer in solids, click solid 1. In the settings window for solid, locate the heat conduction solid section, which is right here. From the K list, choose user defined. So our thermal conductivity will be user defined, and then this is lambda effective. So that was another variable defined in the text file we uploaded. Locate the thermodynamic solid section, and from the row list, choose user defined. And again, we're going to put row effective to call the variable, and then finally CP is going to be user defined, and we're going to call this CP underscore effective. Alright, heat source. In the physics toolbar, click domains. So I'm going to click on physics up here. Domains is this blue icon, and choose heat source. So this will add a condition down at the bottom underneath heat transfer physics. In the settings window for heat source, locate the heat source section right here. And in the Q0 field, we're going to type the expression negative m dot, or the rate, m dot meaning I'm assuming you know what I'm saying. Okay, heat flux. In the physics toolbar, click boundaries and choose heat flux. So now we want to apply a heat flux condition to the boundaries. So there we've got a second one. Oh, I need to select the domain. Okay. If you skip this step here, it will, and lastly, select the domain 1. Now we're adding heat flux for boundaries 2 and 4, so that is our imagining a cylinder that's actually over in this space. So when we define the boundaries as the right and bottom, it's actually the entire bottom of the cylindrical container and the entire outside of the cylinder. but since it's axisymmetric, we're looking at a rectangle, and our boundaries become 2 and 4. So 2 is the bottom, 4 is the right. And the settings window for heat flux, locate the heat flux section at the bottom. I'm going to choose convective heat flux instead of general inward heat flux. And the H text field, type HQ. And the T external text field, type TH. So there's our heat flux condition defined. We've got at the boundaries, the heat source defined for the entire domain. Now we need initial values since we have a time-dependent study here. Time-dependent. If it were stationary, well, we're doing time-dependent. Okay, in the model builder window, click initial values. And the T text field, type T0 or T0. Next, define the coefficient form PDE interface for the liquid phase evaporation. So we're jumping down to the next physics module, or mathematics module rather, and we're going to click on coefficient form PDE1. In the settings window for coefficient form PDE, locate the diffusion coefficient right here section, and in the C text field, type capital DL. It was a variable we defined, so you could go look up what that value is. Locate the source term section down here, and into the F text field, type the expression negative m dot over rho L. So if you recall from the background, here we go. Source term m dot over rho accounts for the loss of solvent as it evaporates. All boundaries are prescribed as no flux conditions. Okay, so this term that we just defined here, negative m dot over rho L, is this last term, and this term is important because we've got a contained system here. So if all boundaries are prescribed as no flux, we don't have any mass going in or out of the system on all 4 boundaries. But you do have liquid disappearing, right? Because you've got evaporation happening somewhere in here, and then as the vacuum drying process progresses, it's coming off the top as a gas. So this term, the source term, F, is a negative because we're losing solvent as it evaporates, going from liquid phase to gas phase. M dot is the rate of mass change. It's negative because we're losing mass from the liquid phase over the liquid phase density. Alright, and then initial values for the PDE. In clicking on initial values, in the settings window for initial values, locate the initial values section and the theta L text field, type theta L0. Set the mesh to extremely fine to better resolve the evaporation front in the domain. So now we're doing the mesh. In the model builder window, under component 1, comp 1, click mesh 1. In the settings window for mesh, locate the physics controlled mesh, and we're changing this to extremely fine, which is the finest element size you can choose, and build all. Okay, because it's a simple geometry, that took less than a second. Box, you can see the mesh that it created has a it consists of 6,250 domain elements and 258 boundary elements. Now we're ready to study. In the study toolbar, click show default solver. Study toolbar at the top, and the solver button is this flags with 4 flags icon. Show default solver. The dependent variable scaling for theta L is manually set to 1. This provides a better convergence. In the Model Builder window, expand the solution 1 node. In the Model Builder window, expand study 1. And you did that. Okay. And then we're going to choose dependent variables 1 and dependent variable theta L. Alright, so the field components, it says default value is comp1.theta_L. Internal variables are comp1.uflux.theta_L and comp1.deflux.theta_L. Okay, in the settings window for field, locate the scaling section. And we're going to change this from parent to manual. Step 1, time dependent. In the Model Builder window under Study 1, click Step 1, Time Dependent. In the settings window for time dependent, locate the study section, and from the time unit list, choose H. We're changing from seconds to hours, and our output times in a range is going to be from 0 to 70 in unit or in increments of 1. In the study toolbar, click Compute. Now we're going to create some surface plots and look at the results, interpretation, and then we'll be done. So when it generates the your surface plots, it's actually going to plot the entire, well, not the entire cylinder, but it's going to create a sort of like a Miss Pac-Man. So you can see the entire cylinder when you're looking at this. Now your contour plots are going to be 2D, so that will keep the rectangular dimensions. And so we've got 2 3D plots and 2 2D plots here, defaulted. In the Model Builder window, under Results, click 2D Plot Group 3. So this is our surface plot of the dependent variable theta L. We've got our scaling over here with the red color legend around 35 times 10 to the negative 4. Okay, and we're going to the data section, and from the time hour list, we're changing this from 70 to 30. So we're going to look at 30 hours and plot. Okay, so there's our roughly halfway, not quite halfway mark. At 30 hours, this is what the surface plot looks like for theta L, which was our volume fraction of liquid. Okay, so next we're going to look at temperature. Looks like that's all we're doing for that plot group. So in the Home toolbar, click Add Plot Group and choose 2D Plot Group. So we're going to Home, Add Plot Group, and we're doing another 2D Plot Group. So we've got 2D Plot Group 5 that appears down here. So in the settings window for 2D Plot Group, type temperature in the label and locate the data section. From the time drop-down menu, we're going to choose 30 hours again. Right-click temperature and choose surface. So we're right-clicking on that, choosing surface. So this was just defining the data set we're looking at. So the data that we'll source for this plot is from study 1, solution 1 at time equals 10 hours. And now we're defining the surface plot that we want to look at. Locate the coloring and style section. From the color table list, choose heat camera light. So it's defaulted to rainbow, and you can pick from all these color schemes. So this says to choose heat camera light. So we've got this nice purple to yellow. So we've got 295 Kelvin on the center of the wet cake, and around the edges of the wet cake we've got the highest temperature at around 330 Kelvin. In the home toolbar, click Add Plot Group and choose 2D Plot Group. In the settings, we're going to type apparent moisture diffusivity, right? In the label text field. Locate the data section, and once again, like our other surface plots, we're going to look at 30 hours. And then the expression, oh no, that's all we're doing here. Okay, so now we're adding the surface plot for apparent moisture diffusivity. So we're going to right click, choose surface. We can create a surface plot for that data set that we just set to source. Locate the expression section, and in the expression text field type DL. In the apparent moisture diffusivity toolbar, click plot. Alright, so you can see, I was wondering if that would change automatically. So before, the expression was temperature and add units of Kelvin. So it automatically puts the correct units when you put the expression in here. Okay, so we've got DL, the apparent moisture diffusivity, in units of square meters per second at time equals 30 hours. And on the high end here, we've got 45 times 10 to the negative 9 meters squared per second. That'll probably be more useful in centimeters squared per second. I mean, you could change the units if you really wanted to, I guess. Let's see, meters squared, so I can't do that in my head. Well, anyway, we've got zeros on the outside of the wet cake and the high end of moisture diffusivity at the center and top of the wet cake, which makes sense because there's not going to be anything diffusing where it's dry. It's already dry on the outside where the heating element or the heating fluid is surrounding this container. Alright, so there's our surface plot for apparent moisture diffusivity. And lastly, we're going to create a surface plot for evaporation rate. So once again, just like the previous steps, home toolbar, add a 2D plot group. This one's going to be called evaporation rate. Time at 30 hours again. So that's sourcing our data, right click, add a surface plot. The expression is going to be m dot and plot. And there you go. And you could look at different times if you wanted to. So you wanted to look at 30 hours and then you wanted to look at the end of that period, 70 hours. So you can see how it progresses. And it's not in here, but you could also do an animation. So you could go to results, animation, player. So let's look at the evaporation rate, the last one we made, and the sequence type. We use the stored solutions, loop over time selection. So you could do either from list, let's just do all. And let's see, number of frames, 25 seems fine. And let's play that to see what it looks like. Alright, so if you want it to play more than once so you can kind of get a better feel for it, you can do repeat. Let's not do forever. How about repeat 3 times? Display each frame. 0.1 seconds is a little too small. How about, or actually let's try a higher number of frames to get a better resolution. And so that's just a little slower. And we've got it playing 3 times. So you can see it starts out red on the outside, so there's a very high rate of evaporation, and then with time, let me play it again, that evaporation front pushes towards the center of that wet cake, because remember we're looking at an entire cylindrical wet cake, until the vacuum drying is complete, and then you see 0 across the entire wet cake because there's no more vapor phase, or there's no more liquid phase left to go into the vapor phase. So the vacuum drying is complete and you have 0 everywhere. Alright, so that was a fun little example. I hope you learned something, and if you want to see more COMSOL tutorials, please hit subscribe, like, comment, and share this video with a friend. It does help get the video out there, even if you don't really want to share it with someone. If you just hit the share button and copy link, it can't tell the difference. So it's helping me out, and it's absolutely free to do that. So I'd appreciate it, and I'll see you in the next video.